Next, we will hear from Professor Yuejie, who will be giving the plenary talk for the Machine Learning and Statistics session. Dr. Yuejie is a professor in the Department of Electrical and Computer Engineering and a faculty affiliate with the Machine Learning Department and Scilab at Carnegie Mellon University. She received her PhD and master's from Princeton University and her bachelor's from Tsinghua University, all in electrical engineering. Her research interests lie in the theoretical and algorithmic foundations of data science, signal processing, machine learning, and inverse problems with applications in sensing and societal systems broadly defined. Among others, Dr. Chi has received the Presidential Early Career Award for scientists and engineers, the inaugural IEEE Signal Processing Society Early Career Technical Achievement Award for contributions to high-dimensional structured signal processing, held the inaugural Robert E. Doherty Early Career Development Professorship, and was named a Goldsmith Lecturer by IEEE Information Theory Society. Please join me in welcoming Professor Yuejie to the LIDS Student Conference.
All right, thank you so much for the very nice introduction. And thank you so much for inviting me. It's my great pleasure to be able to talk to all the very talented students at the LIDS lab and sort of talk about our recent work on understanding the non-asymptotic statistical and computational guarantees for some of the model-free IO methods. All right. Oops, let me just make sure. All right, so I want to start by sort of thanking my wonderful collaborators along this line of work, particularly Yuejie Chen, Yuting Wei, who are currently now at UPenn. We have been really working very closely in shaping this line of research in the last couple of years with our students and other collaborators. All right, so reinforcement learning, as many of you are probably aware, is sort of a very popular machine learning paradigm these days, where agents try to learn by actually interacting with the environment. So typically the agent, for example, this mouse in this maze trying to find maybe a piece of cheese, the environment is typically unknown to the agent, and the agent has some sort of reward or goal in mind, and the goal is really try to maximize its total rewards through a trial and error fashion by interacting with this environment in a sequential and online manner. So there has been a lot of recent success stories about IL in the news recently, ranging from beating humans in gameplay such as Go, StarCraft, to robot controls. And more recently, I think Google is also using IL to design AI chips. So it is sort of fair to say that IL holds a lot of promise in the next era of artificial intelligence. Understanding IL on the other end, or generally improving the performance of IL, face a lot of challenges. Some of the well-known ones include, for example, you always have to sort of think about this dilemma between exploration and exploitation, because the environment is unknown. So you have to sort of either being sort of greedy about the current best policy or being sort of long-term planning about trying to explore things that you're not very familiar with. There is also a problem about the so-called credit assignment problem, because you typically do not get the rewards for your immediate actions that may be really beneficial to you. For example, you're currently all doing maybe a PhD or studying in school without actually making a lot of money, but bear in mind, you may have a sort of a delayed reward in the long term. So you are really doing the right thing. Finally, the world is large and you have many different actions you can take. How to deal with this enormous data and action space in IL is also very challenging to make the method really scalable and sort of efficient. From an optimization perspective, you could think of this as sort of value maximization problem, and the problem typically comes with this non-concavity issue that make it hard to find the global optimum of the problem in hand. All right. So two issues I will be really focusing in understanding it. One is the sample efficiency, because typically in real world applications, collecting data tends to be very expensive or time consuming, especially in problems where you really do not have a sort of simulator where you can sort of generate an infinite amount of training data. Examples like this includes, for example, clinical trials or sort of sending online ads to users trying to discover which ads you really like. So we really need to design sample efficient IL algorithms. Another issue I will be paying attention to is to understand the computational efficiency. So if you look at a lot of the successful IO algorithms in the literature, they often take a lot of time and space in order to work. You may require many GPUs or TPUs and computing hours before you can sort of settle on a good policy. And this sort of putting a lot of resource constraints on our end. So we really want to find computationally efficient IO algorithms. In fact, many of sort of the pioneering work in this sort of dynamic programming or reinforcement learning world was conducted in the LIDS lab. And a lot of this pioneering work in the early 80s and 90s really sort of focusing on what I call the asymptotic regime, where typically the focus is put on sort of understanding the asymptotic convergence and the convergence property of these algorithms. In more recent years, there has been sort of a shift in terms of attention to really understand the finite time and finite sample guarantees of some of these reinforcement learning algorithms by leveraging tools from high-dimensional statistics and high-dimensional probability. This is often necessary because doing finite time analysis allows us to understand more fine-grained performance comparisons of different algorithms where they may both converge asymptotically, but converging at different rates. So getting non-asymptotic results is kind of key to understand the sample and computation efficiency in modern IL problems. Typically, there are sort of two approaches to IL. When you sort of want to convert the sample or experiences you are collecting from the environment to a policy you want to execute. One approach is this model-based approach, where you typically try to first build an empirical model of the environment, and then sort of invoke a classical dynamic programming algorithm to do planning. This is sometimes also called a plug-in approach. Another approach, which is actually going to be the focus of today's talk, is this model-free approach, which typically try to learn without constructing the model explicitly. This type of approach has been widely popular and successful in practice, but have been relatively sort of underexplored, and the understanding is relatively sparse until very recently. So we're also going to sort of focusing on the model-free approach in this talk. In particularly, we'll be looking at both value-based approach and policy-based approach. So in a value-based approach, our goal is to try to learn the optimal Q function. And here I'll talk about what is the sort of finite sample complexity of this Q learning algorithm. In the policy-based approach, the goal is to directly learn the optimal policy by doing some sort of first-order optimization methods on top. And here I'll be talking about sort of what is a finite time convergence guarantee when invoking first-order optimization methods to learn the optimal policy. All right, so with that, I'll first jump into some sort of basic backgrounds on Markov decision process, just to make sure everyone understands the model we're using. And this is sort of the standard model people often use to model the interaction between the agent and the environment, where the agent is typically be modeled by using some sort of action space. So the agent can take actions from the action space, and the environment is modeled by the state space, and the environment can be specified by elements in the state space. And whenever the agent makes an action, the environment pushes a reward, which is a function of the state and the action. And we're going to assume the reward function is a number bounded between the unit interval. The agent wants to sort of design a policy or action selection rule, which can be roughly thought as a probability distribution over the action space when you're fixing the state. And the environment will be changing whenever action is taken, and the next state is drawn from these transition probabilities, which can be thought as sort of probability distribution over the state space when you fix the current state and the current action, right? So an important function we are going to use frequently is this value function that sort of helps to sort of gauge the quality of a policy pi. So imagine you are currently at initial state S, and then you sort of roll out a sequence of action following this policy pi, and along the way you're accumulating a sequence of rewards. An infinite horizon discounted setting, the value function is defined as a sort of discounted infinite sum where future rewards are discounted by the factor gamma, which is called the discount factor. So roughly speaking, you can think of this factor 1/1 minus gamma as effective horizon, where after this effective horizon, essentially rewards collected in the future carry sort of a small influence on your value function. And this is sort of if you look at finite horizon problems, you can often think about the finite horizon sort of is in parallel to this effective horizon, infinite horizon problem. Another function we'll be using is this Q function. So the Q function is very similarly defined, except that instead, besides just fixing the initial state, we are also going to fix the initial action and then roll out the follow-up actions according to the policy pi. So the Q function is sort of two-dimensional table along both the state space and the action space. All right. Now, with these value functions in mind, we can actually now define what the goal of IL is, which is simply just try to find the optimal policy that gives you the highest value of these value functions. If you know the model, this sort of is classically falls into the realm of dynamic programming and optimal control, where a lot of the pioneering work are done in the LIDS lab. However, if the environment is unknown, this falls into this so-called reinforcement learning realm, where you have to actually figure out the sort of the environment as you are sort of collecting data and executing your actions. In terms of notations, we're going to put a little star on these quantities whenever we are talking about optimal functions. All right. So what has been really, really important in understanding Markov decision processes is this sort of Bellman operator, which is really sort of an operation you can apply on top of current Q function estimate by sort of doing this one-step look ahead or bootstrapping. And two important quantities that sort of you want to, properties you want to bear in mind, well, that will be really useful in the rest of the talk, is that one is the optimal Q function is actually the unique fixed point of the Bellman operator. Another important property is this Bellman operator is actually contraction, is a contraction operator in terms of infinity norm. Between, if you apply this to a pair of Q functions, the distance between their infinity norm is actually contracting at a factor gamma, where gamma is a discount factor. So if you know the model, you can actually write down the Bellman equation and try to find its fixed point and find the optimal policy. All right, so that's sort of very basic background knowledge about Markov decision process and sort of how to use Bellman operator or Bellman optimality equation to find the optimal policy. Now, based on this, we're going to now delve into sort of the model-free IL methods by first talking about the Q-learning method, particularly understanding its sample complexity and sort of benchmarking it against the minimax lower bound to see whether it is minimax optimal. In doing so, I need a data generation mechanism. And one of the sort of the simplest model one could use is so-called generative model or simulator model. For this generative model, this allows you to sort of probe or inquire any given state action pair. And this generator model will sort of access the transition kernel and pop up what the next state might look like. We are going to first consider this so-called synchronous setting, where we'll be able to actually probe all the state action pairs simultaneously at every iteration, and do this, say, at n times, right? So that will give us a Q-learning algorithm with n iterations. So with this generative model in hand, this sort of bypass the issue of exploration in Q-learning, but just focusing on the exploitation aspect, understanding to what extent you could exploit the system to get a sample efficient algorithm. Right. Now, So it turns out that people really already understand sort of what's the mini-max lower bound if you try to solve the IO problem in this sort of generative setting. But a very nice paper by Aza in all about 10 years ago now. If you look at what this result is saying is that if you want to find the optimal Q function, say up to some epsilon accuracy in terms of L infinity norm, the number of samples you need is at least this order, which is SA divided by 1 over gamma to the third order times epsilon square. Okay, so there are both good news. There's some actually good news about this result. Oops. In the sense, if you look at this sample complexity, which only scales with the product of the state and action space, it actually can be much smaller than the number of parameters you need to specify the entire transition kernel, which has a size of the square of S times A. So this means that you could actually have very efficient IO algorithms where the number of parameters, the number of samples you need is much smaller than the number of samples you need to actually accurately estimate the model. Now, with this sort of mini-max lower bound in mind, we now want to look at the Q-learning algorithm and see whether it can actually sort of hit this mini-max lower bound. So what is a Q-learning algorithm? So this is a classical algorithm that can be thought as sort of a stochastic approximation method for solving this Bellman equation. So recall what this Bellman equation is. It's really just a fixed point equation where the Bellman operator directly uses model information by sort of averaging over the transition kernels, right? Of course, when we are sort of interacting with this generative model, we do not have the information about the transition kernel directly, but have to rely on samples to build some sort of estimates. And when we are using estimates, we want to be a little bit conservative in making progress. So roughly speaking, the update rule for the Q-learning algorithm at every iteration T is sort of a weighted combination of the previous Q value plus a new term that is built based on this empirical Bellman operator computed by the current samples. So this QT here, oops, mouse is not in my favor today. So this QT here is basically an empirical version, a sample version of the optimal Bellman operator, where we replaced the expectation over the transition kernel by the samples. And eta t is sort of the step size in use that tells you how much you want to be making progress as an iteration to trust the sort of the newly collected samples. Okay, so I haven't tell you anything new yet, just setting up the stage. All right, so let's look at a little bit of prior art in terms of what we know about the sample efficiency of the Q-learning algorithm if I want to achieve an L infinity error of about my optimal Q function estimate up to some accuracy epsilon. There turned out to be already a lot of prior work in this domain. And the state-of-the-art results sort of in the last 2 years sort of pinned down a upper bound about the sample efficiency of Q-learning that scales roughly on the order as A divided by 1 over gamma to the 5th order times epsilon square. All right, so all the parameters are sort of optimal with respect to the size of the state space, action space, and accuracy, except the effective horizon. So the prior art sort of has a scaling about the effective horizon up to the 5th order. However, the minimax lower bound, as we have shown, has a dependency about the effective horizon only to the 3rd order. So this sort of creates a curious question in terms of, can we actually close this gap, right? Is a prior result sort of tight? If they are tight, that indicate Q-learning will be suboptimal, or is this sort of artificial analysis artifact that we can actually improve the sample efficiency guarantee of Q-learning algorithm? So with this question in mind, we actually did sort of a refined analysis of the sample complexity of Q-learning. And our result says that if you constrain your accuracy level within sort of 0 to 1, we can actually show Q-learning will achieve epsilon accuracy as long as the sample complexity is on the order as A divided by 1 minus gamma to the fourth order times epsilon square. So this strictly improves the dependency with respect to the effective horizon by 1 order. So we improve the order from 5th order to the 4th order. And this result actually holds as long as you are using step size that's sort of within a reasonable range, and this sort of accommodate both the constant step size and the rescaled linear learning rates. So both of these step sizes are actually used in the prior art in achieving the dependency about the effective horizon to the 5th order. And this step size are sort of been shown to be really sort of good choices in terms of the theory aspect to get good sample complexity results. All right, so it seems we are getting closer to the minimax lower bound, right? We are no longer at order 5, but now at order 4. But we know the minimax lower bound actually has an order of 3. So we're not quite there yet. So are we really getting the best result possible? We look at a curious numerical example, which I was actually observed in an early paper by Martin Wainwright. And he looked at this very toy example where you only have 2 states in this Markov chain, in this Markov decision process. But one of the state actually has sort of 2 exactly same actions. So no matter which action you are taking, you will get exactly the same reward, the same outcomes. But in this very simple toy example, if you run Q-learning on top, the empirical performance of Q-learning indeed has a sample complexity that scales to the 4th order with respect to the effective horizon. So this seems to be implying maybe the 4th order dependency is really necessary for Q-learning to achieve epsilon accuracy, for Q-learning to work. And that seems to be some algorithmic lower bound. And this is exactly what we did. And we did sort of construct an MDP, which is slightly complicated, slightly more complicated than the one used in Wainwright's numerical example, just for the sake of making the analysis a little bit simpler. We added a little bit of auxiliary states in the MDP, but it's still very simple. And for this particular MDP, we can show Q-learning at least need an order of sample that scales to the 4th order with respect to the effective horizon. So this is an algorithmic dependent lower bound, meaning this is sort of tailored to the analysis of Q-learning. And again, this lower bound also holds regardless of the choice of the learning rate rules you want to use. It holds both for the constant learning rates and the rescaled learning rates. All right, so now we sort of close the loop. If you put together both the upper bound and lower bounds that we have established for the Q-learning algorithm, you can see we really pin down the sample complex of Q-learning that has a dependency with respect to the effective horizon to the 4th order. And this is higher actually than the minimax lower bound, which only has a dependency to the 3rd order. So what this is really saying is Q-learning is in fact not minimax optimal because of the gap with the minimax lower bound. And you might wonder why Q-learning is suboptimal. Despite that there is no sort of rigorous theoretical establishments about this fact, there has been actually a lot of empirical study about this so-called overestimation issue of Q-learning in the literature, ranging from very early works in the 90s to the more recent works on sort of double Q-learning, for example. So here I'm actually taking a picture from double Q-learning where you could see that this issue really comes from the fact that in the Bellman operator, we have this sort of thing that we're taking a maximization over an expectation of some random variable. But this quantity is easily overestimated, meaning you will have high positive bias whenever you are replacing this expectation by its empirical samples, empirical estimates using a small sample size. In fact, this figure I took from this double Q-learning paper suggests that this overestimation issue will become exacerbated when you have more and more number of actions. In the construction of the lower bound, we take a very simple case where we only have 2 actions. But the issue can be even more serious when you have more actions. And this is exactly the reason why the paper by Hasselt introduced this doubling trick in order to solve this overestimation issue. Despite this sort of negative news in terms of the suboptimality of this vanilla Q-learning algorithm, there's actually has been also positive news that this issue is not hard to fix. You could actually introduce in some very simple algorithmic tricks, such as variance reduction, to make Q-learning prove linear minimax optimal. So this has been done again in this paper by Wainwright, where he introduced variance reduction that's originally used in the stochastic optimization literature to improve the sample efficiency of Q-learning to the order of minimax optimal. Okay, so I want to also talk a little bit about TD learning, which can be thought as a special case of the Q-learning when the action space is only a singleton. And this makes the problem much easier because now we don't need to take this maximization over all the possible actions. And this also actually eliminates the issue of overestimation because we now no longer have the nonlinear max operator in it. If you look at this TD learning algorithm, this sort of follows a similar reasoning of Q-learning, except we're replacing the sort of Bellman operator by this simplified version that sort of only look at the value over the states. And this term here is called the temporal difference, which sort of measures the difference about sort of the projected value of the state and the current value of the state. All right. So if you look at TD learning is in fact minimax optimal, meaning that if you want to get epsilon accuracy to estimate the optimal value function, the sample size is only scales with respect to the effective horizon to the 3rd order. Right. So this actually matches the minimax lower bound and suggesting TD learning is actually near minimax optimal. And this is done actually for the vanilla TD learning algorithm, meaning there is no need to do any sort of averaging or variance reduction in order for TD learning to become minimax optimal. Again, our result here accommodate both the constant step size and the rescaled linear rate step size. As the focus here has been really on the sort of generative model or simulator model, I want to also mention about this very important setting that's more close to what is done in practice, where the data actually is collected in a Markovian setting. So one of the case is this asynchronous Q-learning algorithm, where we can imagine the data are collected over a Markovian trajectory by following certain behavior policy, which is not necessarily the optimal policy. And the goal is to learn the optimal policies through running Q-learning algorithm on top of this Markovian trajectory. We also have a paper in analyzing the sample complexity of this asynchronous Q-learning algorithm, where basically the sample complexity will be sort of specified by some sort of properties regarding the Markovian chain. And in particularly, one thing I would like to highlight is that the sample complexity is actually sort of not depending very critically on the mixing time of this Markovian chain, meaning that if you look at the term that includes the mixing time of the Markovian chain, this term actually does not depend on the accuracy. So if you have a high accuracy in mind, as you run the algorithm long enough, the cost from mixing is actually become amortized over the running of the algorithm. And the first term is really very similar to the complexity you get from the generative model, except this mu min is going to be replaced, playing the role of the SA term, 1 over SA term, which is the smallest entry in the stationary distribution of the Markovian chain. Right. So that sort of covers the thing I would like to cover in sort of the sample complexity of Q-learning. I want to just pause briefly to see if there are any questions. I wasn't able to monitor the chat, so just want to see if there are any questions. All right, so if I don't hear any, I'll leave all the questions to the end of the talk. So now I'm going to move to sort of the second half of the talk, which tries to understand the finite time convergence of policy optimization algorithms and how to accelerate some of the basic variance lift. So roughly speaking, this policy optimization approach sort of falls into this very generic optimization framework where you want to be able to maximize the value function, which is your objective. And this value function is sort of parameterized by some policy using parameter theta. And then you can try to directly optimize this policy by sort of doing some sort of search over the parameter space theta. So this approach is very flexible because it directly optimizes the object of interest, which is a policy that the agent will be executing. And this actually also is very useful, especially if you have a hybrid problem with both continuous and discrete variables. This allows you to use some very flexible differentiable parameters of the policy. And then very conveniently, you can embed these methods with, for example, advances in deep learning by running sort of backprop to optimize these policy networks. All right. Now, when we move to sort of theoretically understanding policy optimization algorithms, despite its heavy use in practice, there has been actually very little understanding, especially regarding the global convergence of these policy optimization methods until very, very recently. And one of the reasons is because these problems are typically highly non-concave and making it very hard to argue about global convergence of these methods, following sort of the classical mindset of optimization. Nonetheless, with recent advances in non-convex optimization, and by focusing on very concrete problem instances such as MDP models, we can actually get some very nice understanding about the global properties of these policy gradient methods. So in this talk, we'll be trying to talk about some finite time convergence rates of these popular heuristics. And based on these understandings, we'll try to even design some new variants that are fast convergent and also can help to find policies with desirable structural properties. All right, so what is policy gradient methods? Bear in mind that the objective in mind is this value function, right? And the value function is defined over a per state fashion. So in order to convert this into an optimization framework, I need to aggregate all the states into a single scalar I can optimize. So by doing, to do this, we introduce this initial state distribution rho and average the state over the distribution rho to get this single scalar metric we want to optimize. And typically, because of policy, when you fix a state, it's a probability distribution over the action space, which is give you some sort of constraint problem. And in order to drop these constraints, people tend to use this softmax parameterization, which is very popular if you're looking at sort of multi-class classification problem in supervised learning. So it's very similar. We want to sort of use this softmax parameterization by reparameterize a policy using some parameters theta, which is unconstrained. And in doing so, we essentially arrive at an optimization formulation where we want to maximize over this parameters theta with respect to the value function. And the policy gradient method is simply a very simple first order optimization method where we try to update the parameters theta along the ascent direction of the value function with respect to some step size eta. All right, so what do we know about the global convergence property of this softmax parameterized PG methods? There has been a very sort of nice work and pioneering paper by Agavo al. In 2019, where they show that the softmax PG method actually converge to the global optimal policy in an asymptotic fashion. This is a nice result, but it doesn't really tell us how fast we can get to the optimal policy. Another follow-up paper by Mellon in 2020 shows that softmax indeed converts to the optimal policy within a number of iterations on the order 1 over epsilon, where epsilon is optimality gap. However, this rate also comes up with some unclear dependency with respect to the problem dimensions, such as the size of the MDP and the effective horizon. So it is actually now clear if this sort of finite time convergence rate of PG is actually a good rate or bad rate, given these unclear dependencies with respect to all the salient parameters in my problem. All right. In a paper last year at Code, we actually convey a somewhat negative message about the efficiency of the softmax PG method in terms of rate of convergence. We actually constructed a horrible MDP in the sense, if you run your softmax PG on this MDP we constructed, it can take a number of iterations that scales on the order of s to the 2th power to the effective horizons power. In order to achieve some sort of, in order to drive your, say, our infinity error to some small constant. So what this is saying is that indeed you could find instances of MDP where this softmax PG can take super exponential time to converge with respect to the state space and the effective horizon. And this is particularly bad when the problem has a long planning horizon or large state space. And the result holds even when you start from a good initial distribution rho that sort of is exploratory in nature over all the states. So the issue is not about the initial state distribution that you are using in finding your gradient. And this also holds if you want to use a relaxed goal by only looking at the average suboptimality gap. The same bound will still apply for a slightly different construction of the MDP. Okay, so what is this terrible MDP? I'm not going to explain the details here, but the key ingredients is we are going to construct a MDP that sort of has this hierarchical structure where the horizon size is roughly, this H parameter is roughly on the order of the effective horizon. And we have this important states, says from 1 to 3 up to H. And what happens when you run this algorithm is you cannot really make the future states finding the optimal action before the initial state finds its optimal actions. So pictorially, imagine you want to drive the optimal, the policy distribution of at state 1 to concentrate on top its own optimal action. As you are doing so, you actually are doing worse and worse for the follow-up states. So that when you move to drive the optimal action for the next stage to optimal, you are going to take a longer time and so on and so forth. And this structure essentially implies, if you look at the convergence time for the states, it actually grows geometrically as the states increases. So essentially, we constructed this in a way, this will grow geometrically at the order of 1.5. And when you add together the total time of convergence you need, this gives you this super exponential time convergence we listed in the theorem. All right, so by this point, we've shown that softmax, although it converges asymptotically, it could be converging in a super slow time. I would like to draw this analogy, a very interesting comic I saw that sort of very relevant here. This is like you want to drive a pumpkin cart, say on the busy street of New York City. Although you can get to your destination, but it may not be the best strategy you want to take. You might want to take another way to get to your destination, for example, by taking the subway, right? So what is a subway in this IL world for policy optimization? In order to boost up the convergence rate for policy optimization, One way is to actually use the sort of the natural policy gradient methods. Instead, by searching along the direction of the gradients, we're going to actually search along this natural gradient, which are preconditioned by the inverse Fisher information matrix. And this really tries to make the search direction relatively invariant with respect to different parameterization of the policy. In fact, a lot of the popular heuristics in the literature, such as TIPO, can be thought as MPG with lens search. Another important booster we are going to use is this sort of entropy regularization, which often is used to sort of promote the stochasticity of the policy by enforcing it not to settle early on in sort of some suboptimal policy. And roughly speaking, this is a regularization technique where you add an additional entropy term with respect to the policy in your loss function, where the parameter tau is sort of the temperature or the regularization parameter of the problem. So effectively, by adding regularization, we can use the same optimization framework, but replace our objective function by this regularized variant. Now, putting together these two tricks on this toy problem of a bandit with 3 arms, one can indeed see that if you look at all the gradient flows and natural gradient flows of these two methods, as you move from the left column to the right column by using natural gradients, you can see this blue curve, its gradient flows is becoming more and more direct to the optimal policy. Well, if you move from the top row to the second row, you can see by adding entropy regularization, the trajectory also become more smoother and more direct to the optimal policy, indicating these two tricks may help you to sort of converge more quickly. So the question is, can we actually justify this efficacy of these two tricks in accelerating the convergence? So this is exactly what we did in analyzing the performance of entropy regularized MPG in the tabular setting, where in this tabular setting, you can actually explicitly write all the update rule with respect to the policy itself, where you can see the policy is essentially being updated as a multiplicative combination of the current policy and sort of a soft gradient version of this policy by using the sort of the value function of the current policy. And the weighted combination is specified sort of by the step size you are using, which is upper bounded by 1 over gamma by tau. And this update rule is actually invariant with respect to the choice of the initial state distribution. And in particularly, if you take the largest possible step size, you're basically dropping the input from the current policy, but only using this soft gradient version to do update. And this gives you the so-called algorithm soft policy iteration. All right, so what is the convergence rate of this algorithm? To begin, we are going to assume we have the exact oracle, meaning I can perfectly evaluate this policy, these Q functions given the policy, for example, by using models. Later, we'll relax this that allows you to actually estimate these values using samples. In this scenario, we can actually show this algorithm actually converges linearly to the optimal function, but the soft version, because now we're adding regularization. And the nice thing about this result is that there's actually no hidden constant or excessively large constant. Everything is crystally clear. In particularly, if we now want to interpret the results in terms of infinity convergence to epsilon accuracy, if I'm using a general learning rate, essentially the algorithm converges linearly with iteration complexity scales on the order 1 over eta tau, where tau is a regularization parameter. So the larger tau you are going to use, the faster it will converge. If you use the largest possible step size, essentially the number of iteration you need to take is the effective horizon. And this actually matches the iteration complexity of the classical policy iteration algorithm where you actually do not have any entropy regularization. More importantly, these results are global linear convergence results where all these rate results are almost independent with respect to the size of the state space and the action space, in sharp contrast to the policy gradient methods that we talked about earlier. So to really show its benefit. Let's do some ablation studies. If we remove the use of natural gradient and compare it with entropy regularized PG, in the previous papers, in fact, this suffers from similar issue as a softmax PG without entropy regularization. The iteration complexity, although it's sort of has linear convergence, but actually there's also this unclear dependency with the size of state and action spaces, which can be actually exponential. So by using this NPG, we actually achieve dimension-free rate, which is much faster than the one without using natural gradients. Similarly, if you compare this with the NPG methods without entropy regularization, the vanilla NPG method, as established in the paper by Agavo al., actually converge at a sublinear rate on the order 1/epsilon. Here, we are actually converging at a linear rate, although it's important to say that we're actually solving a slightly different problem by adding regularization. Nonetheless, this helps to sort of maybe understand why entropy regularization has been observed to enable fast convergence in practice by converting a sublinear rate to a linear rate. All right, so so far the results are established, and when we have, assuming we have the exact oracle and perfect model evaluation. We also look at the case when we have inexact oracle by looking at this case, if we have some maybe sample-based estimators that can give us a Q function estimate that are accurate only up to some accuracy of delta. And when we run our entropy regularized NPG method, we're going to use this inexact policy evaluation. I want to see whether the method is still robust with respect to this imperfect policy evaluation. Without getting into a lot of the details, the answer is yes. And in particularly, if you want to use this entropy regularized problem as a way to solve the original unregularized problem, you often are going to set the tau sort of on the order of epsilon. And then that means you want to make sure your policy evaluation also has an accuracy scales roughly on the order of epsilon times 1 minus gamma. And if you use fresh samples at every iteration, this essentially boils down to a sample complexity like such for finding the optimal policy in the original MDP. So this is not optimal with respect to the dependency of effective horizon. And it's actually interesting to see how this result can be tightened up by, for example, reusing samples across iterations. I guess because of time, I'm not going to talk about a lot of the analysis. But one thing I want to sort of say just 2 words is about the soft Bellman operator. So I said early on, the Bellman operator is really, really important. In fact, for this entropy regularized problem, you can define a similar object that we call the soft Bellman operator that incorporates this entropy regularization in its construction. And you can see that the soft Bellman operator actually inherits the 2 nice properties, where this optimal Q function again is a fixed point of the soft Bellman operator. And this soft Bellman operator also contracts at the gamma rate. So with this in place, if you analyze this entropy regularized NPG in the extreme case for soft policy iteration, you can essentially just copy and paste the proof you have for policy iteration, where you do this dance between the policy update and the Q function updates to the case of soft policy iteration by just replacing the Bellman operator with the soft Bellman operator. So this really builds a connection between this classical policy iteration algorithm to the sort of policy optimization using sort of this gradient methods. When you move to the general learning rates, you need to be a little bit more careful. And this is actually a very interesting analysis that go no longer than 1 page. So if you're interested, I encourage you to read our paper. And at the end of the day, we essentially construct a linear system of 2 dimensions where the spectral radius of this 2-dimensional matrix tell us the convergence rate. All right. So moving a little bit beyond entropy regularization, I want to mention a little about our recent work on sort of generalizing this regularization approach to other type of regularizers with the hope that we can actually learn policies that has certain important structural properties to us. So for example, if I'm interested in cost-sensitive IO problem, where not every action costs you the same amount of money or resources, you may want to weight the cost of different actions by using a weighted one-knob regularizer. If in this regime called the constrained or safe IO regime, where your policy may not be able to visit certain action space, or you want to visit those places in less frequencies, you may want to use a log barrier regularizer on your policy. So there are a lot of other possible regularization schemes you may want to use in order to promote desirable properties of your policy. This turns out can be done in this more general framework of regularized IO, where we simply replace the entropy regularizer that we used before by this more general form of regularization function, which will allow it to be convex, but can be possibly non-smooth. And you can essentially follow the same line of thinking by writing down this optimization problem. So how do we solve this more general problem? It turns out it might be beneficial to look at the entropy regularized NPG through a slightly different lens of mirror descent by thinking of it as a mirror descent algorithm with KL divergence, where the KL divergence is in fact the Bregman divergence with respect to the negative Shannon entropy. Okay, so if we take this line of thinking, I can actually generalize this mirror descent thinking to this to solve this more general regularized IO problem. But instead of using the KL divergence in the policy update, I can use this generalized Bregman divergence with respect to the regularizer in use. And this generalized Bregman divergence requires me to update this subgradient of my regularizers, where we can actually find a very efficient way to update this recursively. The details are all in the paper. And this algorithm is actually inspired by a paper by George Lan, where he introduced this algorithm called policy mirror descent, where he also tries to look at this broad class of regularized IO problem. In his algorithm design, the difference from ours is he did not adapt the use of this Bregman divergence term, but maintain the KL divergence in the algorithm, while we choose a Bregman divergence term that is actually in accordance with the regularizer in use. In doing so, we actually can achieve linear convergence for general convex and non-smooth regularizers, while the PMD method introduced by George requires stronger assumption in order to achieve linear convergence. So empirically, we also had done some experiments to demonstrate indeed our GPMD algorithm can often converge faster than the PMD methods. So because of time, I'm not getting into the details of the algorithm. You can look at our paper for its sort of full algorithmic development as well as its theoretical convergence guarantees. This sort of entropy regularization idea and the use of this natural gradient or mirror descent approach turns out to be also useful when you go beyond the single agent MDP. So in a recent NeurIPS paper, we actually look at this zero-sum two-player Markov game, and we consider entropy regularized variant of it. And here we see that you can actually solve the value iteration of this Markov game by using this OMWU, which is a type of actual gradient methods. And with the help of entropy regularization, we actually get much simpler analysis. And we end up having simultaneous all these nice properties where the convergence rate is dimension free. We have last iterate convergence guarantees, and we allow the two players to carry out symmetric updates throughout the execution of the algorithm. So I don't have time to talk about this paper, but if you are interested in the game setting, you can look at this paper from last year's NeurIPS. All right. So with this, I think I'm going to come to the conclusion of the talk. So I certainly talked a lot But mostly the focus here is try to understand model-free algorithms, both in the value-based space and in the policy-based space, in terms of non-asymptotic performance guarantees, both in terms of sample use and in terms of time use. And I think this is a very interesting research direction. A lot of the works are very recently done in the last couple of years from the literature, not only from our group, but also other groups. And I invite you all to sort of jump into this very exciting field to really make progress in this very important problem. In terms of future directions, a lot of the work here are really focusing on the tabular setting, and really understanding the functional approximation setting is very important. There are also quite a few other IO regimes that are worth investigating, such as the offline IO or batch IO problems, and also the multi-agent IO problems, and many, many more. So if you're interested, here are some of the papers we published in this field, and I talk about in this talk. You can find these papers on my website, and I also want to thank my funding agencies, without whose support none of this are possible. With this, I want to conclude. I'll welcome any questions you have, and thank you so much for your attention.
Thank you so much for the talk. So right now we'll open it up for questions. So feel free to raise your hand using the reaction button, and then you can unmute yourself and ask your question, or you can put it in the chat. And I'll start us off with the question. So you discussed in one of the bounds that it was very specific to using new samples at every time. And you said there might change if you're reusing those samples. This was on slide 48. What exactly would change in the analysis if we're reusing samples as opposed to using new ones at every step?
So if you reuse the samples, it may create some sort of statistical dependencies across the iteration of the algorithm. And that may change the analysis significantly, right, from a statistical perspective.
Okay, and
if you use fresh samples, you have independence at every iteration, so things become easier. Okay.
I guess, is there any benefit to reusing samples, or is it just to be complete in the analysis?
So if you reuse samples, you have a smaller sample complexity, right?
Yeah.
Because the number of iterations are essentially the effective horizon. So if you reuse samples, you shave off one factor of the effective horizon. Okay. Generally, it may not be optimal anyway. So as you can see in this model-free algorithm I'm talking about, including Q-learning and the policy gradient methods, the goal is to solve the original MDP, they actually do not hit the minimax lower bounds. We actually have another paper that we showed if you use model-based approach, you actually can hit the minimax lower bound. So model-based approach can be shown to be probably minimax optimal. Well, all these model-free algorithms I talk about here are actually not minimax optimal, at least for now. So there's, I guess there's a lot of open questions in terms how you want to improve this model-free algorithm and what are the benefits and the trade-offs.
Great, thank you. Are there any other questions? If not, I have one more question. You discussed for the worst case, this is early in the first half of the talk, a worst case MDP with a hierarchical structure would lead to, I think, an exponential, exponentially number of samples. Does this kind of MDP, does it arise naturally in problems like a hierarchical structure? And if so, like what would that kind of problem look like? Or is it very specific constructed for the purpose of this analysis?
That's a very good question. So I think it's half and half, right? The hierarchical structures certainly arise because it's credit assignment problem, right? That the sort of myopic things that work for the current state you are in may not be the optimal for the future states you are in, right? So this sort of hierarchical things certainly arise. Now this particular construction we have looks quite daunting, I would say. And this really happens because while you are doing analysis, you kind of add in small things to make the analysis easy to go through, so that it looks quite complicated. So this particular MDP certainly does not exist, right? But it's sort of construct for analysis purpose. But I think generally, if you look at the problem arising in practice, you do observe a lot of slow convergence of the softmax PG method in practice, particularly in compared to this natural gradient variance. A lot of the popular methods in practice as TIPO, PPO are actually all using natural gradients. And that sort of maybe help to demystify why these natural gradient variants are more efficient, more popular in practice, because even in this tabular setting, they have convergence rates that are dimension free, while the softmax PG tend to have more complicated dependencies with problem dimensions to make them less efficient.
Got it. Thank you so much. All right.
Thank you for the question.
Of course. If there's any other last minute question, we can get that. And if not, we're going to end this plenary session and we'll be starting with a coffee break. So please join me in thanking Professor Schiff for coming and giving this plenary talk and kicking off the conference. Thank you so much.